Hi everyone, this is your struggling CS student, and today let's solve another LeetCode problem of the day. Let's take a look at today's problem. Maximize the minimum powered city. 2528 is a 2200 rated question, so it's going to be a very challenging question for me. Okay, let's take a look. You're given a zero index integer array stations of length n, where stations of I represents the number of power stations in the ith city. Okay, each power station can provide power to every city in a fixed range. In other words, if the range is denoted by R, then a power station at city I can provide powers to all cities J such that the absolute difference between I and J is less than or equals to R. And I and J is between 0 to n minus 1, so it doesn't loop around. That's what this line of code is trying to say. So it's like not a circular kind of thing, right? It's like linear. Okay, note that the absolute of x denotes the absolute value. For example, 7 minus 5 and the absolute value of that is 2, 3 minus 10, absolute value of that is 7, okay? The power of a city is the total number of power stations it is being provided power from. The government has sanctioned building k more power stations, each of which can be built in any city and have the same range as the pre-existing ones. Now, given two integers r and k, return the maximum possible minimum power of a city. If if the additional power stations are built optimally, note that you can build k power stations in multiple cities. Okay, let's take a look at some examples. Stations, right? 1, 2, 4, 5. This denotes the number of stations in CDI. Yep. And this denotes the range of the station. So in this case, the range would just be like this. Is that right? I minus j less than or equals to r. Yes, that's right. And you can build k stations in k more power stations. Actually, can be built in any city and have the range as the pre-existing ones. You can build k power stations in multiple cities. So it's not like you choose one and you build k of them. You can actually spread out k number of stations, the new ones, in any of the ith cities. Okay, so let's see. Given this input, the output is 5. Why? One of the optimal ways is to install both the power stations at city 1. So city 1 is provided by 1 plus 4 equal 5 power stations. Oh, city 1 is the index 1, okay. We want to maximize the minimum power of a city. City 4 is provided by 5 plus 0 power stations. Okay, so the answer would be 5, 9, 13, 9, 5. I see, okay. Here you can prove that we can make the minimum power of city greater. It can be proved that we cannot make the minimum power of a city greater than 4. Okay, because the radius is 0, that means a station can only supply a power to its own city. So if you build 3 here, okay, then if you build 3 here, yeah, well, like 1, 1, 1, what the power you get is 5, 5, 5, 4, and the maximum of the minimum of them, 5, 5, 5, 4 is 4, so the output is 4. Okay, there are 10 to the power of 5 stations, and station of I can go from 0 to 10 to the power of 5, and the radius can go up to n minus 1, and k can go up to 10 to the power of 9. Oh my days. Okay, okay. Let's compute the power of this city. Let's take a look. So here, it will be provided by these two, so that will be 3. Here, 2 is provided 1 from here, and 4 from here, and 2 from here, so that's 1, 2, 4. That would be 7. Here it's 2 plus 4 plus 5, that's 11. This is 4 plus 5 plus 0, that is 9, I think. Yeah, and here's just 5. Okay. So in example 1, they claim that, you know, if we build the 2 stations here, right, that's because we want to maximize the minimum power, of a city. Hmm. Hmm. Okay, so initially I was thinking, okay, why not we just, take the minimum city, right? We take the minimum city. I mean, we take the city with the minimum power, and we just build a station there. But actually, it's strictly better to just build a station here because it gives you more choices in the future. Because you're just increasing the power for more cities, right? Why build a city here to increase its power when you can build it here, when you can increase this tree power? If you just build it here, you can only increase the power of these 2 cities. So the claim is that after we build one, mm, build say build station at city 1. This is the input. We'll just put it here. This is the power. This city at station 1. So increase the power here for 8, and this is 12. Right. Then we build the station again at city 1. We get 5, 9, and 13. Is that right? 5, 9, 13, 9, 5. 5, 9, 13, 9, 5. That is correct. That is correct. Okay. How would we do this? The thing that comes to mind immediately is to recognize whenever we are like trying to maximize the minimum value or minimize the maximum value, this falls into one of the pattern where you have to do binary search on a solution space, right? Mm, I'm not gonna explain what binary search on solution space is, but it's a little bit like I don't really have a good example. But if let's say, you have a value, um, you have like a set of values from like x to y, right? And there is a division. There's a division in which the values from, let's say, let me erase this. Maybe I call this z, right? Oh shit. This is z and this is y. There is a division of values where these values are always possible and these values are always impossible, right? Right. So here, it's not really problem solving, uh, uh, in as much as I'm just like recognizing the pattern I'm not sure if this is actually the solution, but this is only like one of the possible ways that we can solve it. So let's see how we can apply this pattern to this problem, because that's the only way that I can think about doing this problem. So usually when you want to maximize or minimize something, there's really only three ways to solve it. Okay. You can there is a greedy strategy that gives you the locally optimal answer and which results in a globally optimal answer. That's greedy, right? Then the other method is actually dynamic programming where you might not make the locally optimal move, but you can break the problem into subproblems such that the optimal answer to a subproblem depends on the optimal solutions to each subproblems. And from there, you can derive the optimal answer. You can make like a locally non-optimal move that can result in a globally optimal answer. That's dynamic programming. The other way would be to do binary search on the solution space, which is what I'm showing here. And I think that is one way we can approach about this problem. So we would say, what is the we would say from this input array, what's the minimum power that we can achieve? Well, the minimum power in this case, x would be 3, right? But what's the maximum power? What's the maximum power that we can achieve from this? I would say, if you build k stations on the maximum element of the array, that would be the maximum. That would be the maximum. Okay, so from there, you derive a range of values. Okay, derive a range of values, then you say z will be equals to 13, right? So we try to guess a value. We say, okay, mm, are we, okay, just to illustrate the example a little bit more, are we able to achieve a power of 3 from the original input array? Well, the answer is, of course we can, because that's the minimum power, right? Then in that case, let's say we try to guess at a number, because the answer here is 5. We would say, we would do a binary search. We would say, okay, 13 plus 3 is 16 divided by 2, which is 8. So we say, okay, we set y is equals to 8. Then we say, can we achieve a power of 8, by distributing this in a greedy manner? So we iterate through this and note that because the radius is 1, really then it's like a sliding window, right? Because each station can extend out to I minus j less than equals to r, which is this formula here. So you can extend out like this and like this. So you can think of it as a sliding window of length r times 2 plus 1. R times 2 plus 1. Yeah. So in this case, it will be a sliding window like this. Then we need to keep track of the elements here. We have to say, if the minimum element, if the minimum element is less than the value that we guess, okay, we need to increase its power somehow. And I think we have to be careful. I think we never want to like you would think, oh, maybe a simple loop like this would do. We just see if this is lower than that, we just build a station there greedily. But I actually think we might need to build it in an optimal manner. So what do I mean by that? Suppose the array that you get is like 3, 7, 3, 9, and 5, right? If you only have 2 stations and you build the 2 stations here, you change this to 5, and you change this to 9, and then you say, oh, I ran out of stations to allocate, right? And then you say, actually, the value 5 is actually not possible if you somehow guess the value to be 5. And then your answer would just return 3. But we will see that actually the answer is still 5. It's still 5. Yeah, this might not be a very good example. This might not be. How can we get like a 37395 power? So you have one here. You have 1, 2, 4. Yeah, it's not a great example. Maybe like 1, 2, 1. If it's like 1, 2, 1, 1, 2, 1, 37395 example. Yeah, I don't think is that even possible. So these have to be the bigger value. These have to be the bigger value. So it's like maybe like 1, 2, 1. In that case, that would be like this is 3. This is 4. This is 3. For this to be 9, it has to be like this is 0 and this is 9, right? Then you have like 9, 9 here. Yeah, yeah, 3. So 1, 2, 1, 0, 9. Let's try that. Is the answer also 5? Hmm. Okay, so like you can see here, from this distribution of power, okay, where your k is equals to 2, and your radius is 1, right? You can't just greedily allocate the power here and say, allocate the station here and say, okay, um, you do 5, 4, 3, right? You have to do it in a manner where you actually allocate it here, where it's so it becomes 5 plus this. So it's 3 plus 2, 4 plus 2, that would be 6. Mm, mm. Then this is 5, and then this is 9, this is 9. Okay, so coming back to this question, we have to do it optimally. But how? How do we do it optimally? That is really the question. I think it's not that bad at all. I think it's not that bad at all. So instead, we what we care about would be then the center, would be the center of each point, the center of each point. So instead of like checking in at index 1 onwards, what we will do is the check would. So we'll have like a sliding window like this. Okay, and then we say uh, we check the minimum value here. We would always add to this range. We will always add to this range. Hmm. As in, sorry, like we would always add this. So we would consider this point, this point, and this point for r equals to 1. So if let's say the minimum value here it's less than or equals to 8, we will allocate that many amount of stations there, right? So if at any point in time our k is less than 0, we're done because there's no way we can actually reach this power. And you can see it forms a impossible area where, if you can't even with given case stations, you can't even achieve a power of 8. There's no hope achieving a power of 9 or 10 or even 13. So the answer must lie in this area, this solution space. So I think the pattern actually matches. I think that is the way to approach the problem. So you would say, but how are we going to keep track of the data structure? I think we can put this in a heap, a sliding window, put this in a heap. Oh, that's like a combination of like a lot of different concepts. So in a window, we need to keep track of the minimum power. So we have 7, 11. We have 3, 7, 11. This is our heap. And we say, hey, what's the minimum power here? Well, we have to increment this. Therefore, increment this. I see. Okay. The challenging part is how can we update this value? I I think you need to keep track of the minimum and the maximum in a window. So the problem becomes, you know, uh, so the smaller problem becomes, given an input, given a input, you need to keep track of the minimum maximum value of a window or fixed size that you know, and then you need to keep track of the minimum and the maximum element as you traverse out of the window. Okay. When I always think about that, I think of like monotonic queues. So let's say you have like 3, 7, and 11. Okay, then your minimum is here and then the maximum is here. Cool, cool. Then you say, okay, if the minimum is less than this, you need to allocate this amount. Suppose the value that we are guessing is 5. In this case, because the minimum here is 3, we need to allocate 2 in this range. So in that case, our minimum will become 5, and our max, this is the min, this is the max. It's a bit hairy, isn't it? Yeah, it's a bit hairy. You update the max? You update the max here, do you? I guess you update the max, right? To be 13. I mean, that's the only solution I've got, so why not we just watch your head? Okay, cool. Not sure if it'll work, but let's try it. Let's try it. So we'd say the minimum value would be the minimum of stations, and then the maximum value would be equals to the max of stations plus k. So while the minimum is less than equals to the max, this is okay. Misclick, that's left, this is right, this is our binary solution search space. We are returning, what are we returning? The maximum possible minimum number, so we are returning the minimum. Okay, then we will do a check, mid is equals to L plus R whole thing divided by 2. If can achieve, I guess, achieve power of mid. If we can achieve it, that means we want to minimize it. Is that it? Yep, we want to minimize it. So right is equals to left minus 1. Else, well, if we can't achieve the power, we have to raise the power. L is equals to R plus 1. Okay, so this is the key function that we need to implement. Can achieve power given a certain power. Okay, so we need build a monotonic queue. Do queue like this. Then we say for station in stations. For station in stations, so the min and the max is always the front and the back of the queue, which for double-ended queue you have access to. While q and q of -1 is greater than. So what we want to maintain is the maximum, how should I say it? Sorry. So this part is, I should explain what a monotonic queue is. So a monotonic queue can either be like monotonically increasing or monotonically decreasing. What does that mean? What that means is that given a sequence data structure like a list of numbers like 1, 3, 7, 10. This means this list is monotonically increasing. That means the values is always like going up like this, right? Okay, wait, that was a bad graph. You'll be basically it just goes up. Okay, there's never a point where it dips like this. A monotonically decreasing queue or some sort of sequence data structure, it means the other way around, right? So if you want to be like very very precise, okay, this is actually monotonically strictly increasing. Some people say a monotonic increasing, that's the only definition. So it doesn't account for values that are equal like this. So some other people will be like super precise and what they will say, this is monotonically non-decreasing. Because this is not strictly monotonically increasing, because you can see from one element to the next, this point, they are equal, so it's not increasing. Yeah. So that's what a monotonic queue or a monotonic stack is. So how does this help you? Well, a monotonic queue allows you to keep track of the min and max elements for a window of elements, and a monotonic stack or monotonic queue, whatever, it also helps you to keep a sorted sequence of numbers in a particular window or in a particular range of elements in a sequence. So okay, so here for station in stations, right? Well, queue and queue of the one is greater than station. We'll do queue dot pop. Otherwise, if length of queue is greater than r times 2 plus 1, this is the window length. Then we do q dot pop length. So this maintains the. Oh, never mind. It's not good enough. We actually need the index actually. Enumerate stations. So now, if stations. So the reason is because we can't just use the length of the queue to check the window length. We actually have to use the indexes themselves to keep track of the length of the current window. Yeah. So now our queue stores the index of the value instead of the value itself, right? Mm, mm. So now we can then calculate what is the size of the current window. So the size of the current window would be q minus 1, minus q of 0 plus 1. So that's the current window size. Current window size exceeds the window line, where we would q dot left. Otherwise, we'll q dot 10 I. And then we need to return a true or false. Okay, so we need to check the current minimum and the current max. Current min is equals to q of 0. Current max is equals to q of -1. So we would say if the current min is less than our power, that means we need to increase the power to match the whatever power we are guessing, right? And that's the input. We would say needed is equals to 0. Needed plus equals power minus current min. Now, because we have applied the additional power here, we need to update the current max. So in that case, we say q dot pop. Then we say q dot 10. Current max plus this. Current max plus power minus min. Is that correct? It should be inside here. This is the difference. So needed plus equals the difference. Current max plus difference. Return needed is less than or equals to k, because there's only so much k stations we can build. So needed keeps track of the wait, I think I have to be careful. I think I have to be careful when constructing the sliding window. Let's see. Okay, so when do we do this check? Yep. We only do this check. Wait a second. We only do this check when we have reached the window length. Otherwise, we will just pop. If we exceed it, we just pop it. Otherwise, we are less than the window length. We would oh, it's not a if, it's a if. It's a if, yeah. So if we exceed it, we have to correct it. After we correct it, we need to do the check. I think. Oh my days. Let's try it out. DQ index out of range. Hmm. There's nothing in the queue. I see. It's because here I'm appending the max, but I do not want to modify stations itself. That means I need to actually store, my queue need to store a tuple of the index and the power itself. Here I'm appending the index, but here I'm appending the max. I mean the value. So that's why you get this index out of bounds error. So in my queue, whenever I append, I need to append both the index and and the the value itself. Then in that case, I can just check on the value itself. So here that will be 0. This is also 0. The QL 0, QL left, current min is, this is 1, this is 1. Current min is less than power minus current min, needed plus equals. This is the current max and index j, I guess. J equals to current max dot q dot pop, q dot append. This is a tuple of j. Oh no. No, we got the value itself, so we don't need to refer to stations. Oh no. This is 4. This is 0. Oh my days. What is that? Needed to reguess the power of 3. Wait, what? Oh, I see. I haven't even built the power array. Okay, we need to build the power array. Hmm. The stations here is really referring to the power array. So we need to pre-process the input. Okay, it shouldn't be too hard, but I just need to figure out how can we process the input. So we have 1, 2, 4, 5, 0. R is equals to 1. Really? Do I really need to use a difference array here? I think I do. Wait, difference array, how will it work? Hmm. Difference array, how would it work? There'll be like 1, there'll be like because I need to apply a range update to 3 elements here. So it's like 1, 7. No, not 7. This one I need to add 2. This one I need to add. Holy shit! Even pre-processing the input is a big challenge. How would I do that? I need to update the values here. Here, 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 and here. This is +2. This is +5. This is +7. This is +4, and then this is +5. Prefix sum 1, 3, 7, 7, 1, 2, 3, 4, 5. That's 12. It's possible. It's just very troublesome. Okay, so I think we can use perfect sum. So we can say that okay, for this particular element, how can we get like the sum of 7, right? We can we just want the sum of this subarray and this sum of this subarray, right? So for this subarray, we can take it's got a little bit messy. We can take the sum of this subarray minus this one. Then we can get this range. For this one, right, we can take the current sum. We can just take the subarray sum here. Okay, cool. Okay, at least we know how to pre-process the input. But what about this one? For this one, we want the subarray on the right side. On the right side. Okay, okay, cool, cool. Okay, so we need to build the prefix sum first. This would be stations. There's at least one station, so that's good. So station of 0, 1, so length of station power array dot append station I plus power array of -1. Okay, so here we are not enumerating stations, but the power array, and this is power Station power. Naming is hard. Naming is hard. Prime main, let's send the power. Station power. Yep, okay, okay. So we calculate the prefix sum, and then now we need to apply the update. That's not. This is the prefix sum. Oh. This is the power array. That's equals to this. Okay, for I in range of length of station, power array, we say right is equals to length is equals to suppose radius is 2, that means here will be 0 plus 2, so it will be index 0, 1 to index 2, prefix sum of I plus I plus k if I plus k is less than n, else we'll return prefix sum of the last element. Wait, hold on. Minus prefix sum of I plus k minus the current one. Yeah. Left it else this would be prefix sum of minus 1. This is prefix sum of I minus k. No, this prefix sum of I minus prefix sum of I minus k. No, I don't think it has to be so complicated. Yeah. I should call this the right bound. Right bound is equals to the min of have I defined n? No, I have not. That's fine. So we would say n is equals to the length of station it will be min of n minus 1. So this is the inclusive bound, or I plus k. The left bound is equals to the max, the max of I and I minus k. Yeah. Okay. So here, right would be the right contribution would be a prefix sum of the right bound minus the prefix sum of the left bound. Is that right? Okay, let's just do it without the shortcuts. I'm pretty sure you can do it, but let's just do it properly. Okay, so this is right, left is equals to the prefix sum of left bound. No, I think that works. It's fine, I think. Prefix sum of the left bound plus station of the left bound. Yeah. So that is power array dot append, like so. So what this is saying is that you have an array of elements x, y, z, a, b, c. Okay, suppose right is equals to 2, or radius is equals to 2, right? So you have a prefix sum here. So consider this element, right? Let's say I is equals to 0. So we will say the prefix sum would be of the right side would be like this, right? That's the right bound. The left bound, because there's no I minus k, it will be bounded to here, right? So we take the right bound minus the left bound. What we get is this, but we actually need to add this back. So power array dot append this. Let's check if the power array is correct. God dang it. Oh no, that looks very wrong. Seven eleven 711 950. Where's the 3? My days. One, 3, 7, 12, 12. It's not stations, by the way. Okay, 0. Is my calculation wrong then? Looks like my calculation is wrong. I plus k. I plus r. Oh my god. 369. Oh shit. 0 to 1. The left bound is max of I minus r. What's the left bound 1? The left bound should be 2. No, the left bound should be 0. guess at least it looks correct. 313. Yep, I remember this was 13. Yep, okay. 3711. 95. But the answer is 3. Why is that? Keep this in mind. Needed is 0 and the power is 8. Print the power array. The min and the max. So we guess 8. Yep. How can the needed be 0? Oh my days. Okay, let's see. Zero 3 1 7. Then it's like this. Then now we do this check, right? Okay. What? This isn't even executed. Come on, man. Window length. The window length is 3. Yep. 0 3 7 11. Okay, we pop the 9. It thinks that this is the max. But the current window size calculation. Oh. Why does it never reach the window length? 3 7. What the hell? Looks correct. Looks correct. 3, 7, 11. Oh shit, okay. Ah, oh fuck. Uh, needed is 5. Okay. It went out of bounds. I think you take the last element instead. Current window size. Take the last element minus actually check like this. That's the min, that's the max. Then you go here. Oh, that's wrong, isn't it? Shit. So 3, 7, 11. Pop this. Get 9, and we also pop this. We say that the min is this, and the max is this. The min is this, and the max is this. But actually, the max is here. This is the max. So if you want to keep track of the min and the max, there is no way, bruh. There's just no way. Don't tell me you need to use a freaking double heap here to keep track of the min and the max as you go. Really? So as you go towards the right side, you check the top of the heap, and then you say if the index is you know, outside of our whatever, we'll pop it out. Then we'll get the new min, which is here. But not only that, you know, we're also keeping track of the maximum element in a particular range. I think you need to use a double heap of a monotonic queue. So let's do that. And from there, you can use a sliding window approach. That would be a lot simpler, I guess. Uh, the so mean heap is the station power and the index. For the max heap, it's a negative station power. Okay. If I minus k, I minus k is it's not k, it's r. It's this one. Window length. So if I minus window length is greater than or equals to 0, so 0, 1, 2, I plus 1. Greater than 0, 1, 2. 0, 1, 2. 0, 1, 2. Just I plus 1. Okay. So at index 2 plus 1 minus 3 is square window length, that means we have a valid window. So it needed so for the power that we're guessing minus the mean heap, if the mean heap cannot reach that power, we have a difference power, right? So we add difference to what we need. Okay, to what we need. Then we say if the difference is greater than 0, we have to update the maximum as well. The maximum will be updated. This is fine to update the maximum heap like this because whatever's at the top of the heap is already a maximum element, so adding it will also maintain the heap property. So we need to update it like in this case, right? So 0, 1, 2, 3. So I minus r, 3 minus radius, 3 minus radius, so 3 minus 1. Oh shit. 3 minus the window length. So this is the index at the top plus the window length. Suppose this is the minimum. So when we consider this element, you need to do a check at the top. Okay, you know what? Let's just keep this simple. Let's just keep this simple. Uh, uh, for I in range of the window length, right? We would do this. Okay. Then we'll do a check like so. Min heat. If the difference greater, I'll update it as well. Okay. I in range of window length, hit push, station power, show you the power array, I. I minus window length. Okay. You piece of shit. I can't use the I here. No, why is it like that? Okay. Hey, what is this? Oh? How can that be? I think I need to update the min as well. Oh shit. Okay. Mm, mm. Okay, you know what? I think this is too much. It's too much because I'm thinking of a case where, you have um you have like three you have like three 7-Eleven. Yeah, I think it's time for me to give up this question. Oh man, I feel like conceptually I got it, man, but it's just too hard. It's just too hard. Binary is such a difference array? Really? The fuck? Okay, I definitely have to study this. Definitely have to study this. But I guess my intuition was at least right, but the implementation, yeah, maybe not the second part where I keep track of the min and max. Yeah, yeah. Anyway, thanks for watching this video. And if you stayed so long, yeah, I was like racking my brains trying to solve this one. Well, I couldn't. It is what it is. You live and learn, right? So thanks for watching, and have a nice day.